Okay, this is the notes for Unit 1, Day 7, and they start on page 17 of your packet. So today's focus is going to be limits involving infinity. So we know infinity is that sideways 8, right? The symbol. And infinity, of course, means a number that is so far away from 0 that we don't really give it a value. And so that's what we're talking about, is how do we find limits when infinity is involved? Okay, so our central question then is, how do limits describe asymptotic behavior? So you might guess that infinity and asymptotic behavior are somehow related, and you'd be right. So just before we get going here, because we need to talk about some behaviors, and this function comes in handy, you should know what this function looks like. Remember, I keep drawing it in the air in class, and I make a little sound effect, right? I draw it in the air and I go, right, that little sound effect. So that's what that shape looks like. And we know then that these are two very useful limits. Okay, so here's limit as x approaches 0, right here. This limit is 1 for sine x over x. And if it were sine of 5x over x, it would be 5. If it were sine of 12x over x, it would be 12. So those are some variations. But look at this limit, right? We kind of talked about it a little earlier, but here's where we're starting to sneak in a discussion about infinity, right? As x approaches either infinite values, plus or minus. So way out here or way out here, we know that this oscillates, but its hills and valleys get closer and closer to the x-axis, so we know these limits approach 0. And we call this end behavior because it's way out at x values of infinity. So we're going to talk about end behavior today in relationship to looking at end behavior as a limit question. And we'll get back to that towards the end of the notes. Okay, so actually, let's go back to that. I have a calculus wall, and these two are on that, and I will add things to that calculus wall all year long. Okay, so limits involving infinity. Then, we get this Mr. Buzz Lightyear here to infinity and beyond, right? So Buzz Lightyear kind of might be explaining the way he's flying, might be explaining end behavior, right? As we go out to infinity and beyond, right? That would be end behavior. And that when we talk about end behavior, we're going to talk about horizontal asymptotes in that scenario. So we are connecting limits and asymptotic behavior. And there's also another kind of asymptotic behavior, and those are called vertical asymptotes. And vertical asymptotes you've already dealt with in pre-calculus and probably even algebra 2, right? Vertical asymptotes are these locations where we have a vertical line and the function approaches it but doesn't cross it. And we already know how to find those locations. So we know that we find these vertical asymptotes when the denominator of a rational function is equal to 0. And so when we talk about that, then that becomes, we'll go back here, that when we have a 0 in the denominator, that becomes a location of a vertical asymptote. We talked about having 0 in the denominator. That means those functions either go up to positive infinity or down to negative infinity. We'll talk a little bit more about that too. So if we go back to looking at our flow chart, just to kind of revisit what we've done direct substitution. Direct substitution, we plug in a value into a function, we get a value out, that's the limit. I say probably, but really with almost certainty. We've talked about approximations using tables and graphs. We've talked about re-expressing, especially rational functions, right? When we get 0 over 0, I know there's a 0 in the denominator here, but remember the 0 in the numerator also makes that special property where we have to re-express these rational expressions functions using these techniques. So if you look at this, there's a lot grayed out already, right? The only thing we have left to talk about is asymptotes and how they relate to limit questions. So look at this rational expression here. B over 0 means I have a numeric numerator, some finite value, but I have a 0 in the denominator. And that's where our vertical asymptote is located. And again, I say probably here, but it is with almost certainty that there is going to be a vertical asymptote there. Okay, so we can probably cross out these probablys at this point. So we are looking for rational expressions that have this form, a number over 0. So let's take a look at this. This is a graph of a rational expression, and you have this in your notes. It looks like this. So when we look at this, we can see that this portion and this portion of the graph are not connected. So we have a built-in discontinuity here. We also notice that this one goes down to negative infinity, and this goes up to positive infinity. So we know that location, we must have vertical asymptotes about here and about here. So we have one vertical asymptote, just visually, it looks like at -3. And we have another vertical asymptote here visually at +3. And we can confirm that by setting this equal to 0 and solving this, right? The square root of x squared minus 9 equals 0. We can square both sides. We get x squared minus 9 equals 0. And then we can either bring the 9 over and square root and get plus or minus 3, or we can factor it into x plus 3x minus 3 and get the plus and minus 3. But this also has horizontal asymptotes. This part of the graph, as we go to positive infinity, it looks like it gets flat. And it looks like it gets flat just visually at about y equals 2. And then same here, it looks like this gets flat about y equals -2. So those are horizontal asymptotes. And we'll find those too. But that has to do with going out to infinity. And I want you to notice this here. I bet you sometime when you were in a math class, your teachers say, oh, well, functions never cross asymptotes. And they weren't really telling the whole story. If you notice the vertical asymptotes, the function never does cross those. And that's really true. But horizontal asymptotes are what we call end behavior asymptotes. In other words, these asymptotes really come into play way out at the ends, at the positive infinity and the negative infinity locations of the graph. And so the fact that the asymptote crosses the graph right here at, basically maybe x equals -3.5 really doesn't factor into the property of the asymptote, because this asymptote really is applicable way out here at negative infinity. So this doesn't matter. So we will see functions crossing horizontal asymptotes all the time. And they do that at places that are so far removed from the ends, they're really close to 0, that it really doesn't play into the property of the asymptote. Okay, let's talk about vertical asymptotes first. So here's the vertical asymptotes, and this is the picture where you just sketched in your asymptotes. So we know the definition of a vertical asymptote, the line x equals a. Remember, these lines have equations, right? The vertical lines cross the x-axis. So the equations for these lines are x equals -3 and x equals +3. So the definition then for vertical asymptote is line x equals a, where a is a number, is a vertical asymptote of the graph of a function if either the limit as we approach a of the function goes either to plus or minus infinity, or as we approach a from the other side, the function goes to plus or minus infinity. So that's kind of, these are one-sided limits, right? As we approach a from the bigger values, or as we approach a from the little values. So the idea is that this vertical asymptote, x equals -3, as we approach it from the littler values, this limit goes to negative infinity. And this part of the function, as we approach +3 from the bigger values, so as x approaches +3 from the plus side, this function goes to positive infinity. So we know that when we take the limit of a function and the answer we get is either positive or negative infinity, we know that this x location must be a vertical asymptote. So, so when there's a vertical asymptote, the limits there go to plus or minus infinity. We have infinite answers, we've got vertical asymptotes. And we'll work with that. Okay, so let's find these algebraically. This is still the same function. So let's take the limit of f of x at each vertical asymptote. So let's look, let's find that vertical asymptote algebraically. So I kind of alluded to this a little bit earlier, just verbally. So we're going to set the denominator equal to 0. And you can't just, now I want to caution you here because I have the square root of a binomial. This is not equal to x minus 3. You can't just square root this and square root this. You can't square root the pieces. Okay, if we have a radical here, we have to, in this case, it's a square root. We have to square both sides to get rid of that radical. So when I square both sides, I get x squared minus 9 equals 0. In this case, I added 9 to both sides. And when I square root, I get positive and negative answers. So I get x equals plus 3 and x equals minus 3. I could have also factored this, right? This is a quadratic. It's factorable. It factors into x plus 3, x minus 3. That's why you get 2 answers. Okay, let's talk about taking the limit at these locations. So I'm going to talk about taking the limit at -3 at one of these asymptotes. So this is what it looks like. And then I'm going to do the positive 3 over here. So if I take the limit as x approaches -3 from the small side, right? So we're approaching -3. So we're starting at maybe like -7, then going to -6 and -5, -4, and we're approaching -3 from the smaller values. Okay, so let's take a look at what happens when we do that. Okay, so I am going to go ahead and plug in -3. And I'm going to see what I get. So let's see, I get -6 plus 3. That's -3 on the top. And I get 0 on the bottom. We know that -3 over 0, this is the b over 0 I was talking about, right? B, some finite value over 0 is a vertical asymptote. Okay, now the fact that this is negative is telling us that this is going to negative infinity. Okay, so this answer is a negative infinite value because of that negative sign. Let's try the positive 3. Remember, this is all going back to that graph that we started in our notes, that we sketched in our asymptotes. So you're looking at the graph, you can see that when x equals -3, we're going down to negative infinity on your graph. Okay, let's try as x approaches positive 3. So as x approaches 3 from the larger values, so we're going to make, this means we're going, maybe starting at 7, then going to 6, then going to 5, then going to 4, then approaching 3. We're going to plug in 3. We're going to do this math. 2 times 3 is 6, plus 3 is 9. This is 0. So we have 9 over 0. We know, again, this is a finite value over 0. This is a vertical asymptote. That's the form for the vertical asymptote in our flowchart. So we know that this is an infinite value. And because this is a positive fraction, we know that this limit approaches positive infinity. And we can see that graphically too from our sketch. So, so limits like this, when we get limits and we get this expression of a finite value over 0, in both of these cases, we know we have asymptotes. We know we have infinite values for the function. So just to recap at this point, if you get a limit value, these are limit values down here, right? That is infinite. It doesn't matter if it's positive infinity or negative infinity. There is an asymptote located at this x location and this x location. Okay, just like we confirmed here algebraically. Okay, so we're switching gears now. We're talking about horizontal asymptotes. We're talking about those green ones now. Okay, these are fun. I like these because horizontal asymptotes, they're horizontal lines. And so we know they have the equation y equals that b value. So in this case, this horizontal line is y equals 2, and this horizontal line is y equals -2. Okay, so y equals b is a horizontal asymptote of the graph of the function of f of x if either is the case, if either of these things are the case. So look at what we're doing here. We're taking the limit of the function as x approaches infinity, and we get some finite value. So as x approaches infinity, that's along this blue asymptote, right? As x approaches infinity, coming down this blue portion of the function, okay, the function value is approaching 2 from above, okay? Likewise, we could also approach an x value of negative infinity. That would be along this portion of the function. So as we're coming to negative infinity on this portion of the function, this function starts to creep back towards -2. Again, a finite value. Okay, so we use the definition to calculate the limit to find those horizontal asymptotes. If you're out at this infinite value for x, you're way out at the ends of the function. Okay, that's your horizontal asymptote. So we don't care that this crosses the function here, because that's not even close to infinity. When we get out way out here to negative infinity, it's never going to cross again. Okay, so that's why we call horizontal asymptotes, that's why we call this end behavior, because we are literally looking at the ends, the left end and the right end of the functions. Okay, so let's talk about the horizontal asymptotes here. So when x approaches plus or minus infinity, gets far from 0, we get a break. This is the cool thing. And we can take some shortcuts mathematically. So this is really kind of cool. So let's take the limit as f of x as x approaches plus or minus infinity. Okay, to find these asymptotes. So we're going to first look at the asymptote located at y equals -2. Which means what we're doing is, since this asymptote is prevalent for x values of negative infinity, that means we're going to take the limit of this function as x approaches negative infinity. Okay, and for the asymptote at y equals +2, that's on the right hand side of that function. So we're going to take the limit of this expression as x approaches positive infinity. Okay, so this is how this kind of rolls out. Let's take the limit as x approaches negative infinity of this function. Now, what this means is that we are I'm going to kind of use some bad math terminology here. We're going to put in x approaching negative infinity means we are at really, really big negative values. That's kind of a bad technique to call it that. But the point is that we are at negative values that are so far away from 0. Those are actually really small values, right? I call them big negatives. So these are the breaks we get. Okay, now when we are really, really far away from 0, think about this. If we are at 10 million, -10 million. For -10 million, 2 times -10 million is -20 million. Adding 3 isn't going to make a whole lot of difference. Same thing here. If we're at -10 million and we square it, subtracting 9 isn't going to make a whole lot of difference. We literally can ignore these constants. We just can cross them out. They're insignificant. So this limit of this original rational expression is going to behave the same. So I'm going to use an approximation squiggle here instead of an equal sign. These are not equal, but it's approximately the same as just looking at this as 2x over the square root of x squared. So we just got rid of these little constants that aren't going to change the values for when we're really far away from 0 anyway. So now, looking at this, we can simplify this denominator. The square root of x squared is just x. So now I'm going to rewrite it as, I'm going to look at this as just x on the bottom. So I have 2 times a negative value on the top. And because I've squared x, I've got a positive value on the bottom. And those values are equal. So those are going to cancel out, and we are just going to get a -2. So that's where we get the -2. That's where we get this equation that y equals -2. That asymptote comes from the value of this limit. Let's look at y equals +2. Same thing applies. We're going to cross out the 3 and the 9 because they're so insignificant and we're way out at the positive end of this function. We're going to look at this. Notice the steps are the same here because the rational expression is the same. But now, since we're way out at the positive side here, we have a positive over a positive x over a positive x. Those cancel out. So now our limit is a positive 2. So this other asymptote then is y equals positive 2. Okay, so we can show this rational expression has these horizontal asymptotes. Really, what we're going to focus on here is this technique for finding these vertical and horizontal asymptotes with some examples. So let's look at these 3 examples. We have a limit here as x approaches infinity. So these are all horizontal asymptotes because we see that we are taking the limit as x approaches infinity. Okay, this is a really, really, really cool thing about these horizontal asymptotes as end behavior. Is I can, like we did before, let me get rid of that so you can see what I'm crossing out. I can ignore the -1 and the 4. Those are just constants. But here's the other really super cool thing. I can also ignore these linear terms, x and -3x, because I'm cubing x way out here. And I can also ignore these squared terms. The only thing that's going to matter is the highest power in the numerator and the highest power in the denominator. Those are the only things that are going to matter when we're out at infinity. So I can boil this really complicated. Let me reverse that for just a second. This looks really complicated, but I can simplify it down to that because I am looking at the end behavior. I'm looking at the limit as x approaches infinity. So I'm going to look at that. Let me disappear those so that we can look at this. I'm crossing out because at this point, x cubed over x cubed, those 2 factors can cancel. And here is my limit, 2/5. So y equals 2/5. This is what it looks like. So what this function looks like, y equals 2/5 is the limit as we approach positive infinity. It happens to be the limit as we approach negative infinity as well. So, so the nice thing is this happens, they have the same horizontal asymptotes that on both ends. Remember our function a little earlier had different asymptotes on either end. This one actually has the same. Okay, let's take a look at this second example. The second example is we're still approaching infinity, and we have this rational expression of 5x plus sine x over x. Okay, now we know that when we have this, we have a binomial on the top and a single term on the bottom, we can actually split that into 2 fractions. And that's really important because this rational expression we can simplify. This rational expression, we know the limit of sine of x over x as x approaches infinity. Remember, that was the graph that I said you should really get used to looking at that, right? It's the graph. So, so we're going to address both of these limits, and then we're going to add them together. So we're going to simplify that. We get 5. And then we're going to look at this. So limit as x approaches infinity of sine of x over x. Okay, look back in your notes to the beginning of the notes. What is that limit? Okay, and that is a value of 0. Remember, that's when the hills and valleys get closer and closer to the x-axis. So this limit then is 5 plus 0, which is 5. And this looks like this. All this looks like is that familiar shape. It's just shifted up 5 units. Okay, let's take a look at this last horizontal asymptote. Limit as x approaches infinity. We have a 5th degree polynomial in the numerator and a squared polynomial in the denominator. We're going to start crossing stuff off just like this. The 1 and the 7 are gone. The next higher powers are gone. And in the top, even the power to the 4th is gone because all we're doing is we're keeping the highest power in the top and the highest power in the bottom. When we're out there at infinity, those are the only things that matter. So that's like looking at this. Now look at this. These don't cancel like these did, right? We've got leftover power on the top. So when we look at this limit with this modified rational expression, we can still cancel, but we still have an x cubed in the numerator, right? We can cancel an x squared with an x squared on the top. And so as x goes to infinity, this goes to infinity, which means if we have an infinite value, we don't have a horizontal asymptote. This just, it's almost like looking at a x cubed, right? Looks like this. And so as we go to positive infinity in the x's on the x value, we're just going to go to positive infinity on the y values too. So in this case, there is no asymptote, and it's because we have infinite value on that limit. Let's go over a few examples I got off the College Board website, the AP Classroom website, and they're good examples where we don't have that really distinct pattern of just having a ratio of polynomials where you can just keep the polynomial with the largest degree on the top and the bottom. They're a little more complicated than that. So let's take a look at example 4 here. Has function g is defined by g of x equals, and then we have a coefficient here in front of a natural log. So the coefficient is a ratio of polynomials. It's x squared minus 3x minus 10 over x minus 5 times the natural log of yet another ratio, x squared plus 6x plus 9 over x cubed. It's a little small, but I think it's x cubed plus 3x squared. So this kind of looks like a ratio of polynomials, and in a lot of respects it is. But it's made more complicated by the fact that we have a natural log in here. And we have a natural log of this ratio. And it says at what values of x does the graph of g have a vertical asymptote? So by inspection, I'm looking at these ratios, these rational expressions, and I'm looking for zeros basically. And I'm seeing that there are zeros at -3 and 0 and 5, which, I mean, you don't even really need to look at that. You could just look at your options down here and come to the same conclusion. So, so already those points are obviously points of concern since they're answer options, really, quite frankly. Okay, so we're looking for vertical asymptotes. We know that's when the denominator is equal to 0. That's what we typically think, right? And it's true in this case as well, to a certain extent. We have ratios of polynomials, so we really should look at simplifying this first. So we're going to do that. Also, we're looking at the natural log, and we have to remember that the natural log follows this basic shape. Okay, so the natural log, as we go to infinity, the natural log goes to infinity, just really slowly. And as we go to 0, the natural log is asymptotic with the y-axis. So the equation x equals 0 is an asymptote. Okay, so this that automatically makes me zero in kind of focusing on B, C, and D. Just with that alone, if I knew nothing more. Okay, so let's take a look at simplifying these. So since they're polynomials, we want to re-express, and so that we can take care of any canceling and getting rid of those holes, right? Because when we have a hole, we know that's our canceling factors. That's not an asymptote. Obviously, we can eliminate those locations. So let's factor the top, x minus 5, x plus 2, right? We need to make a minus 3x and a minus 10. And then the bottom doesn't need factoring. And then we have the natural log, and let's factor on the inside here. We have x plus 3 times x plus 3, so it's like a perfect square. And then if we factor out an x squared here, we have x squared times, x plus 3. So we definitely have some canceling here, right? Those cancel, that's a whole, right? This is just, we can look at this ratio like we've looked at all of the ratios of polynomials, that's a whole. So we know that D is out because we don't have an asymptote where a whole is. And we also have canceling over here. So you might think, oh, well, there's another whole. It's not actually the case. And the reason being is because this is a repeating root. We didn't get rid of both x plus 3's. We only got rid of 1 in the numerator. So this in all likelihood is not a whole because we still have a factor of the same magnitude left. So we got to look at that a little more closely. And this is going to tie into what's happening with the natural log. Okay, so we've eliminated D. And we're going to look at -3, x equals -3 a little more carefully. So let's look at the types of discontinuities. So We know we can get rid of 5, but let's look at x approaching -3, and let's look at what this value is. So in this modified expression, when I plug in -3, I get -1 times the natural log of 0. Okay, and we know, going back to knowing what natural log looks like, the natural log of 0, when the stuff in the brackets equals 0, we have an asymptote. That's the natural log of 0 doesn't exist. Natural log goes to -infinity as x goes to 0, or as the stuff in the brackets go to 0. So that being the case, this goes to -infinity, this is -1, -1 times -infinity is +infinity. We know that any limit that goes to infinity means I have an asymptote at this location. So that's a vertical asymptote. So now we know that it's 0 because of this canceling, and I'll talk about that in a second. Excuse me, it's not 0 because of that canceling, it's 0 because of the natural log, and we also know that it is -3. But let's talk about that scenario at x equals 0. We're going to do the same thing. We're going to plug in 0, okay, and we get 2 times the natural log of something that's undefined. So we know that also goes to infinity, right? Because the natural log of 3/0 is the natural log of infinity, and when x goes to infinity, we know the natural log also goes to infinity. So this is 2 times infinity, which is infinity. And again, by definition, if we have a limit that's infinite, then we have a location of a vertical asymptote at this location. So we know that's a vertical asymptote as well. And then just for kicks and giggles, we've already eliminated 5 because of the canceling here and no x minus 5 factor left. But let's just plug in 5 to this modified limit. And we get 5 plus 2 over 8/25, right? If we plug in 5, we get 8. If we plug in 5 here, we get 25. That's just a numeric value. I don't know what it is. I don't really care. I just know it's not infinite. So that's a finite value, so that is not a location of a vertical asymptote. So we have a vertical asymptote at these two locations, 0 and -3, so this answer must be C. Okay, so a little bit more involved. They're good thinkers in terms of questions though. Okay, let's take a look at example 5. So we have let f be the function given by f of x, and this function's a rational expression, it's cosine times e to the 2x minus 1 divided by the quantity e to the 2x minus 1 plus 2. What are all the horizontal asymptotes? So let's just look at what e to the x looks like, right? We got to be familiar with these functions when they appear here. So e to the x is exponential. It has an intercept of 1. So e to the 2x would just grow faster because the power is bigger. So as x goes to infinity, e to the x goes to infinity. As x goes to minus infinity, e to the x goes to 0. So a horizontal asymptote as we go to negative infinity is 0, as the equation y equals 0. So we want all horizontal asymptotes, which means, and let's look at cosine. Cosine oscillates, right? So cosine, as we go to infinity, because we're talking about horizontal asymptotes, as we go to infinity, cosine oscillates all the way out to infinity to the right and all the way out to negative infinity to the left. And since it oscillates, it doesn't have a limit. Okay, so that's what we're dealing with here in terms of limits at infinity. So let's take a look at them as we go to positive infinity. So as we go to positive infinity, we have this. So again, it's knowing, since we're taking horizontal asymptotes, we know we can eliminate any insignificant values because we're way out at infinity. And so when we're way out at infinity, we know e to the 2x is going to be way up at infinity. It's going to be big. And so since these are big, then these are going to be little, relatively speaking. So we are going to eliminate those. That's a bad typo. Hold on. Let me correct that. That should say little or small. Sorry about that. Okay. It's a bad typo. Okay, let's get back to where I was. So those are small by comparison. So we can eliminate those. We're not canceling them, right? We're just saying they're insignificant, so we're not going to write them as part of the expression. So now we have this. So let's think about how we got from here to here. Cosine x stays with us. E to the 2x over e to the 2x minus 1 basically means I have a bigger power on the top by 1, right? Because I have a smaller power on the bottom by 1. So I have a leftover e on the top. So after I get rid of the insignificant values, this we know that this original relationship closely looks like cosine e to the 1. Well, e to the 1 is just a number, right? It's 2.71828, and then some other stuff. So this is going to continue to oscillate with an amplitude of 2.71828. So it's going to go up 2.71828, down 2.71828, up 2.71828 as it goes to infinity. So it's going to continue to oscillate. So it's not going to narrow in on a horizontal, it's not going to level out, so to speak. It's not going to narrow in on a horizontal asymptote. Okay, well, we want all asymptotes, right? See the word all here? So we also need to check negative infinity. And as we go to negative infinity, these powers become negative. And we know that when those powers become negative, if you look at the e to the x curve, that those values go to 0, right? E to a negative power goes to 0. So these become the small ones, okay? And since it's cosine times a small number, cosine can also be ignored. And so these become the relatively speaking big values. And so now we're looking at a value of -1/2. And so we know that as we go to negative infinity, this f of x, this rational expression, flattens out at -1/2. So that is our horizontal asymptote at -1/2 only. So knowing these basic shapes really helps a lot. And remember, I have that graph of, or that anchor chart of basic shapes above the course content at a glance, the scope and sequence for calculus on my wall in my room. Okay, let's take a look at this last one. So let f be a function defined by f of x equals 3 to the x plus 2 over the quantity e to the 2x plus 1. Now this is interesting. For all x greater than 0. Okay, it says which of the following is a horizontal asymptote to the graph of f. So again, we're looking at horizontal asymptotes, but we're only looking at the right end behavior. Okay, we don't care about the left end behavior because we don't care about negative values of x. So this is like half a problem. We only have to look on one side. So let's get familiar with these, what these look like. These are both exponential, right? And I've got them both graphed down here. Okay, 3 to the x is the blue one, and e to the 2x is the greenish one. I think it's green. So if we notice, the exponential e to the 2x grows much faster for positive values of x. So think about this whole expression. The top grows slow, the bottom grows fast. Does that make sense? Okay, top grows, so the top is going to be teeny weeny, the bottom is going to be big, huge, enormous. What value does that go towards? Okay, so think about that. Let's kind of walk through it. Only positive, so we're just going to do the limit as x approaches infinity. So for positive values of x, these both get big relative to the values of 2 and 1. So those things are small. We're gonna get rid of those, and we're gonna rewrite it, excluding the insignificant terms. And again, that's not canceling; they're just gonna go away. And so now we're looking at this. And so if we have enough awareness about these functions to know that the denominator is growing much quicker than the numerator, then what we can say is that the numerator is small, the denominator is big, and that's the same as saying like a number over infinity, which is 0. Okay. That might be a little bit of a stretch, but let's see how we can navigate this to rationalize that. Well, 3 and e are about the same value because e is about 2.71828. So this is roughly 1-ish, but this is really e squared. So e squared now. I mean, think about squaring 2.71828. That's close to 9. So this is actually like 3 over 9 to the x power. Okay, so so if you can think about the ratio that way, that might help. Okay, so let's take a look at these exponentials and let's explain this a little more with math. Okay, and that wasn't all supposed to appear at the same time, but I think I have my animation messed up. So this is kind of what I'm saying, right? This is really 3 over e squared to the x. Well, e squared is 2.718 squared, that's about 9. So this is a ratio that's smaller than 1. And we know that when we have like a half to the x power, that ends up going to 0. So that's one way of looking at it more mathematically, so that maybe you don't have to get too familiar with exponentials and which exponential goes faster than the other. Just a last comment about looking at this though. When we look at the fact that the 3 and the e are different numbers, we really should focus on the powers. So this power of 2x is going to dominate over a power of just x, even if these numbers are different. You know, the powers are all powerful, so to speak. So we know that the bottom then grows much faster. So e to the x, or exponentials in general, grow a lot faster than polynomials. They grow a lot faster than trig functions. They grow a lot faster than just about anything except for x to the x power. That's what grows the fastest. So getting an idea of what grows the fastest and what grows the slowest is a good thing to kind of know. When we get back into the class, we'll go through the takeaways and we'll work on vertical and horizontal asymptotes in College Board.